Hello, my name is Frances Laudiano de Leon. I will be presenting evaluating large language models on multi-word expressions in multilingual and code switch contexts. This work was done alongside colleagues at the University of Bath. So I will take you through the context of our work. I will speak about some of the data sets that we used. I will go over the experimental setups and then go into the results and the implications of our work and conclude. I'm going to begin with defining what is a multi-word expression. It is a linguistic unit of two or more words that function as a single lexical item. Some examples of this include expressions like kick the bucket, spill the beans, strong tea, and credit card. In this work, we will be focusing on expressions such as kick the bucket and spill the beans. These expressions can be either idiomatic or literal. And this will help in our experimentations. Some of the key properties of multi-word expressions are that they are often non-compositional, they have syntactic irregularities, they can be literal or idiomatic, and can be idiosyncratic. So what is our aim? As we all know, large language models perform impressively in zero-shot and few-shot settings, but they do have their limitations. These limitations include hallucinations, a huge problem, and the fact that many of these models rely heavily on statistical co-occurrence patterns. It is therefore our aim to investigate whether these models can understand nuanced language using multi-word expressions as a probe. So why are we using multi-word expressions? Well, they do require a social and linguistic understanding. So the context in which they're being used in, that requires some sort of sensitivity or understanding from the models. They occur across different languages. So we can see whether there's a difference in how a model might interpret multi-word expressions in English, for example, versus other languages. And the meanings cannot be inferred from individual words. So, for example, kick the bucket, when used to in the sense of death, right? Or saying that someone kicked the bucket, someone died. That meaning cannot be inferred from the individual components of that multi-word expression. And what we are trying to do here is to see if LLMs can handle multi-word expressions robustly, which may suggest that if they can, that they are generalizing beyond just surface level statistical associations, especially if they're able to do this in a multilingual or code switch setting. So very briefly, code switching is when individuals use more than one language in an utterance or in a moment of speaking. And we do use code switch data as one of the data sets that potentially will help us explore more deeply whether the models are relying on surface level statistical associations. So the data sets that we are using, we're using the SemEval task 2022 task 2 data set created by Harish Tayar Madhabushi and colleagues. This data set is available in 3 languages, so that is English, Portuguese, and Galician. The organizers of the SemEval task do not release the test labels. So there are lower chances of our models having seen at least the labels of this data through instruction tuning. And we take this data and we use it to create a synthetic code switch data set. And what we do is that we pair Spanish language. So we turn these sentences or phrases into Spanish mixed with Portuguese, English, and Galician separately. So we have a Spanish-Portuguese pair, English-Spanish pair, and Galician-Spanish pair. We generate this data using GPT-4 Turbo 0125 with a temperature of 0.65. We use this temperature because this is a temperature that gets us slightly more naturalistic code switched phrases. And we do release this on our GitHub, which the link of which is available on our paper. And we create this data set because we want to see how well LLMs handle MWEs or nuanced language in a code switch context. Synthetic data, the synthetic data is coherent. It reduces the reliance on surface patterns because the models probably have not seen the Spanish and, for example, Galician co-occurring in that one phrase that contains that one multi-word expression. And it offers an alternative to scarce and costly real world code switch data. So I will take you through our experiments. The setup for most of our experiments is similar, but we're testing different aspects. So in this experiment, the multi-word expression sense disambiguation, we are trying to see whether models can tell us whether a multi-word expression in a certain context is used idiomatically or literally. So these experiments were done in a zero-shot and few-shot setting. The few-shot setting, in the few-shot setting, we gave the model 5 examples, 3 in English and 2 in Portuguese, each with examples, at least one example in using a multi-word expression in an idiomatic sense and in a literal sense. The data used for this was, of course, as I mentioned previously, the SEM-Eval 2022 Task 2 subtask A data, the information of which is available here. And we use that original test split and then the synthetic CS data set. At each case, the few-shot examples were the same, given in a monolingual or mixed language setting. And the prompts generally contained an input, which was the sentence and a target multi-word expression, the prompt itself. And we simply asked the model, can you output whether this is used in an idiomatic or literal sense? So we apply these prompts, 3 base prompts to all the models that we tested. Then we have a synthetic multi-word expression interpretation experiment. So what we do in these experiments is that we want to test whether models can do the same task as what we presented just previously, except for synthetic multi-word expressions. That is to say, expressions that were created using some software to generate nonsense words. So words that these models have never ever seen. These experiments were inspired by Eisenkloss and colleagues. And what we want to see is whether the models can learn new vocabulary through prompting. So given that these multi-word expressions are synthetic and are nonsense words, what we do is that when we're asking the model or when we're inputting or we give it these expressions to the model, we do define it. So an input would be a sentence plus a synthetic multi-word expression plus the definition of that expression. And what we're asking the model is can you interpret this multi-word expression correctly? So can you tell us whether it's idiomatic or used idiomatically or not? And then we have a multi-word expression paraphrase similarity experiment. So here we give the model two sentences and we ask it, and we do tell it that one may contain a multi-word expression. And we ask it to tell us whether these two sentences are similar in meaning or not. And we simply ask the model to output true or false. We do these experiments in a zero-shot and a few-shot settings. And again, we do say to the model, some of these may contain idiomatic expressions. So an example of an input to the model would be sentence 1, she finally spilled the beans. And sentence 2, she revealed the secret. And the model is asked, are they similar in meaning, true or false? Here are some statistics about the data set. We did have to adapt this task. Originally, this was a semantic text similarity task, of which most of the time we ask in semantic text similarity, we ask a model to output a value between 1 and 5, let's say, to tell us how similar two sentences are to each other. In our case, because we're using large language models, we have to adapt this task into a binary one. And we do the task in code switch setting and in a synthetic multi-word expression variant as well. So very quickly, here are some of our results. So for the first set of experiments, the multi-word expression sense disambiguation, GPT-4 is the strongest amongst the LLMs. However, XLMR is the best in Portuguese. And code switch yields some small gains in English and Galician, but the results are mixed for Portuguese. In the few-shot setting, we can see that Llama 370 billion variant improves. XLMR remains competitive, but Llama 3, the 8 billion variant, is a little bit unstable. We see that we're going from a 0.527, let's say in the monolingual setting on the 8 billion Llama to 0.23, and then likewise this decreases in code switch. And then for the synthetic multi-word expression experiments, just want to turn your eyes onto these dotted lines here. This is the random baseline. And we can see that the models only modestly exceed this random baseline. And that GPT-3 seems to be the strongest in this case. And for the paraphrase similarity, so that's that adaptation of the semantic text similarity task. In the zero-shot setting, XLMR is the strongest, there's no question about that. And followed maybe not too closely, but followed by GPT-4. In the code switch setting, all models drop performance. And the XLMR remains the top even code switch. And with GPT-4, we can see that few-shot helps, and with Llama as well. But XLMR, again, is still the best in this case. Code switch remains challenging for the models. So what did we learn about multi-word expressions and LLMs through our experiments? Firstly, LLMs detect idioms well, but underperform a smaller fine-tuned XLMR model. English language is, the models are strongest in English language and not so strong in Portuguese and Galician. Slight macro F1 gains in code switching, likely due to Spanish language mix with English and Galician. It probably helps the model kind of get more meaning. However, they still don't perform very well for Portuguese in these experiments, in the detection ones. Semantics is harder. LLMs struggle with non-compositional meaning. Few-shot examples do help, but it seems like models are relying on spurious correlations and do not beat XLMR which of course I understand XLMR has been fine-tuned, but it is a much smaller model, and these large language models have been tuned on the entirety of the internet. Prompted definition. So when we provide definitions, the performance of the models is still near random. And model size does not necessarily go with model performance. For example, Llama 38 billion is competitive for English language detection in a zero-shot setting, but it is unstable in a few-shot setting. But GPT-4 is robust for semantic understanding. LLMs are showing clear limitations in capturing MWE semantics. Low frequency multi-word expressions remain challenging, highlighting a potential risk that models are memorizing and relying on spurious correlations. And we are also providing that new test and generally a new task to be able to probe nuanced language understanding. Obviously, these experiments can be done with other examples of nuanced language, not just multi-word expressions, but we do kind of put forward what a task doing that might look like. Thank you for listening. If you have any questions, please contact me at my email down here. And yeah, I look forward to hearing from you.